The universe is vast beyond comprehension, filled with countless stars, each whispering secrets we are only beginning to hear. Among them, hypergiant stars stand as colossal titans, radiating energy so immense it defies imagination. Yet these giants don't just shine, they scream. Across the cosmos, astronomers have detected strange, unexplained signals emanating from these stellar behemoths, signals that don't fit any known pattern of astrophysics. Some flicker like Morse code from the void, others pulse rhythmically, as if echoing from depths we can't yet fathom. Tonight, we're diving into 25 of the most baffling signals ever recorded, transmissions from hypergiant stars that leave even the brightest minds in science scratching their heads. These aren't just anomalies, they're cosmic riddles that could rewrite what we know about the universe. So buckle up. What you're about to hear will stretch your understanding of space, challenge everything you think you know about stars, and maybe, just maybe, leave you staring at the night sky with a whole new sense of wonder. Because out there, hidden in the static between the stars, the universe is trying to tell us something, and we are finally listening. Now, let's kick things off with one of the most mystifying signals ever captured, the Eta Carinae Anomaly. This hypergiant star, located around 7,500 light-years away, is already famous for its explosive temper. Eta Carinae is no ordinary star. It's a volatile behemoth prone to massive eruptions that can outshine entire galaxies. But buried within its chaotic outbursts, astronomers stumbled upon something even stranger: bizarre radio bursts that defy every known rule of stellar behavior. These aren't your typical stellar signals. Most stars emit radio waves in predictable patterns, tied to their magnetic fields or surface turbulence, but the bursts from Eta Carinae, they're erratic, flickering in and out like a cosmic strobe light, with frequencies that shift wildly without warning. Even more puzzling, some of these bursts contain repeating structures, tiny, almost rhythmic pulses hidden within the noise. It's as if the star is sending out coded messages, but in a language we don't yet understand. One leading theory suggests these bursts might be tied to the star's violent binary companion. Eta Carinae isn't alone, it's locked in a gravitational dance with another massive star, and their chaotic interactions could be warping magnetic fields in ways we've never seen. But here's the catch: the signals don't match any known binary star behavior either. They're too sharp, too irregular, like nothing we've recorded from other systems with colliding stellar winds. Another possibility: hidden cosmic machinery. Some researchers speculate that exotic physics, like plasma instabilities or even magneta-like activity deep within the star, could be generating these bursts. But without more data, it's all educated guesswork. What we do know is this: Eta Carinae's radio bursts aren't just anomalies. They're a glaring reminder that even the most studied stars in the sky can still surprise us, hiding secrets in plain sight. And if we ever crack their code, it could rewrite how we understand hypergiants and the universe itself. So as we move forward, keep Eta Carinae in mind. Because this isn't just a mystery, it's a cosmic enigma that refuses to be solved. And the deeper we look, the more questions it raises. But that's the thrill of space, isn't it? Just when we think we've got it figured out, the stars laugh and show us how much we still have to learn. Turning our gaze to another cosmic giant, let's unravel the whispers of VY Canis Majoris, a star so colossal it could swallow our sun like a speck of dust. Located roughly 3,900 light-years away, this hypergiant isn't just big. It's a stellar titan on the brink of collapse. Yet, amid its turbulent final act, astronomers have detected something unexpected: faint, rhythmic signals that pulse like a distant heartbeat. Unlike the violent outbursts of Eta Carinae, these whispers are subtle, almost shy, repeating at intervals too precise to dismiss as random noise. What makes these signals so baffling is their sheer inconsistency with how hypergiants usually behave. Stars this massive are notorious for their chaos-explosive ejections, erratic dimming, and deafening stellar winds, but VY Canis Majoris its murmuring. The signals, captured in radio and infrared wavelengths, form a pattern that resembles slow, atmospheric ripples, as if the star's outer layers are vibrating in unison. The problem: current models can't explain how a hypergiant's turbulent atmosphere could produce such delicate, organized waves. One hypothesis points to hidden layers of instability deep within the star. Imagine a pot of water simmering bubbles rise steadily until suddenly they erupt. Some researchers think similar subsurface turmoil, perhaps from collapsing convection zones or trapped magnetic waves, might be generating these whispers. But here's the twist: the signals don't match any known stellar pulsation models. Red supergiants like Betelgeuse throb predictably as they expand and contract, but VY Canis Majoris's ripples are smoother, almost melodic. Another tantalizing idea involves circumstellar debris. This star is shrouded in thick clouds of dust and gas, remnants of its own violent shedding. Could these whispers be echoes, sound waves bouncing off distant clumps of material, creating interference patterns? It's possible, but the math doesn't quite add up. The timing between pulses is too consistent, too clean for random scattering. Then there's the wild card: acoustic resonances. Just as a plucked guitar string vibrates at specific frequencies, hypergiants might harbor sound waves trapped in their atmospheres, amplified by their sheer size. If true, these whispers could be the first hints of a previously undetected stellar symphony, a natural oscillator operating on a scale we've never witnessed. But until we peer deeper, VY Canis Majoris's murmurs remain a beautiful enigma, reminding us that even the loudest giants can harbor secrets spoken in hushed tones. So while Eta Carinae shouts its mysteries, this star prefers a quieter approach. And that's what makes space so endlessly fascinating. The universe doesn't just defy our expectations. It does it with style. Now, shifting our focus to another cosmic enigma lurking in Orion's shoulder, let's tackle the Betelgeuse flare mystery. This red supergiant, a ticking stellar time bomb, has long fascinated astronomers with its erratic behavior. But nothing prepared them for the bizarre flare that erupted in 2019, an outburst so intense it dimmed the star dramatically, only to unleash strange radio emissions that defied all expectations. Betelgeuse is no stranger to drama. As one of the brightest stars in our sky, it's known for pulsing in and out like a slow, cosmic heartbeat, yet this flare was different. Unlike its usual rhythmic dimming, the star's brightness dropped by nearly 2/3 over just a few months, a plunge so steep it sparked rumors of an imminent supernova. But when the dust settled, something even more puzzling emerged. Alongside the dimming, astronomers detected unusual bursts of radio waves, a phenomenon almost unheard of in stars this cool. Here's why that's baffling. Red supergiants like Betelgeuse aren't supposed to produce significant radio emissions. They're too cold to generate the high-energy processes that typically create such signals. Hotter stars like blue giants can produce them through violent stellar winds or magnetic storms, but Betelgeuse, its surface is a relatively chilly 3,500 Kelvin, hardly the environment you'd expect for radio fireworks. So where did these emissions come from? One leading theory points to shock waves rippling through the star's outer layers. Imagine titanic bubbles of plasma surging upward from the core, slamming into cooler gas near the surface. The collisions could generate shock waves powerful enough to accelerate charged particles, sparking radio bursts. It's akin to the static crackle of a cosmic thunderstorm, only on a scale that dwarfs anything in our solar system. But there's a twist. These emissions weren't just random noise. They followed a pattern, flaring up in sync with the star's dimming. That synchronicity suggests a deeper link, perhaps a massive ejection of material that temporarily obscured Betelgeuse's light while simultaneously triggering the radio waves. Infrared observations later revealed a colossal dust cloud near the star, likely the aftermath of such an eruption. Another tantalizing possibility involves magnetic upheaval. Betelgeuse's magnetic field, though poorly understood, could have reconfigured violently, releasing pent-up energy as radio waves. If so, it would hint at magnetic processes in red supergiants far more complex than we've imagined. What makes this mystery so thrilling is its implications. If cool, dying stars can produce such energetic flares, it challenges our very understanding of stellar physics. Could these events be precursors to supernova, or do they represent a previously hidden phase of hypergiant evolution? For now, Betelgeuse keeps its secrets. But one thing's certain, the universe loves reminding us that even the oldest, most studied stars can still surprise us, and that's a lesson worth watching the skies for. Now let's journey from the fiery enigma of Betelgeuse to another stellar spectacle, one that spins a cosmic mystery as mesmerizing as it is perplexing. Meet WR-104, a Wolf-Rayet star whose elegance hides a storm of high-energy secrets. This celestial powerhouse, nestled in the constellation Sagittarius, isn't just any star. It's a whirlwind of violence wrapped in a stunning spiral of dust, and it's been caught emitting gamma rays, the universe's most energetic light, in ways that defy simple explanation. What makes WR-104 so extraordinary? For starters, it's a binary system, locked in a gravitational dance with a hot, massive companion star. Together, they've sculpted one of the most breathtaking structures in space, a pinwheel-like plume of dust spiraling outward like water from a cosmic sprinkler. This dust plume, glowing in infrared light, is the result of colliding stellar winds, hurricanes of gas blasted from both stars at millions of kilometers per hour. When these winds collide, they compress and cool, forming dust grains that catch the light of the stars, creating that mesmerizing spiral. But here's where the plot thickens. Astronomers have detected gamma rays, ultra-high-energy photons coming from WR-104's vicinity. That's bizarre because gamma rays are typically produced by the most extreme events in the universe: supernova, black holes, or pulsars. A dust-shrouded Wolf-Rayet star, not so much. So why is this star or its environment generating such intense radiation? One compelling theory points to those colliding stellar winds. When particles in these supersonic winds smash together, they could accelerate to near light speeds, like cosmic protons in a particle accelerator. These accelerated particles might then collide with photons or other particles, producing gamma rays as a byproduct. It's a natural particle physics lab on a galactic scale, yet there's a twist. The gamma ray signals don't perfectly align with the dust plume's orientation. Some researchers suggest a hidden culprit, a third, unseen object in the system. Could a neutron star or black hole lurking nearby be funneling energy into the mix? If so, its gravitational pull or magnetic fields might be supercharging the winds, turning them into gamma ray factories. Another puzzle is timing. Gamma rays from WR-104 seem to come and go unpredictably. That variability rules out some steady processes like simple wind collisions and points to something more dynamic, perhaps violent magnetic reconnection events or episodic jets blasting from one of the stars. What's at stake here isn't just one star's odd behavior. WR-104's gamma rays could teach us how particles are accelerated throughout the universe, from distant galaxies to our own cosmic backyard. They might even hint at how certain heavy elements, the building blocks of planets and life, are forged in these chaotic environments. For now, WR-104 keeps its secrets tightly wound in that beautiful spiral. But every flicker of gamma light brings us closer to untangling the physics of these stellar powerhouses and reminds us that even the most dazzling cosmic sights often hide the deepest mysteries. Now let's turn our attention to another cosmic head-scratcher, one that bends the rules of physics as we know them. Nestled in the constellation Cygnus, NML Cygni isn't just a hypergiant, it's a star that seems to play tricks with time itself. Astronomers have detected radio signals from this colossal star that arrive later than they should, as if the universe hit a pause button. These delayed echoes don't just puzzle scientists, they challenge our fundamental understanding of how light travels through space. NML Cygni is a monster of a star, one of the largest ever discovered. If you placed it at the center of our solar system, its outer layers would swallow Jupiter. But its size isn't the only thing that makes it extraordinary. When researchers trained radio telescopes on it, they noticed something bizarre. The star's radio emissions didn't arrive in a neat, predictable stream. Instead, some signals lagged behind, echoing like a shout bouncing off distant mountains. But here's the catch: in space, there are no mountains to bounce off. So what's causing this cosmic delay? The simplest explanation would be interstellar gas or dust slowing down the signals. But here's the problem: radio waves, like all light, travel at a constant speed in a vacuum. Even passing through dust clouds, they shouldn't be delayed enough to create noticeable echoes. Yet, the lag observed from NML Cygni is significant, stretching over days or even weeks. That's not just a hiccup, it's a full-blown mystery. One leading theory points to gravitational lensing. If a massive object like a black hole or a dense cluster of dark matter floats between us and NML Cygni, its gravity could bend the star's radio waves, forcing them to take a detour through space. Think of it like light bending around a glass lens, except on a cosmic scale. The longer path would explain the delay, but here's the snag: no such lensing object has been found in the line of sight to NML Cygni. Another possibility involves the star's own turbulent surroundings. Hypergiants like NML Cygni shed enormous amounts of material, creating thick shells of gas and dust around them. Could these chaotic layers be reflecting or scattering radio waves in unexpected ways? Some models suggest that dense pockets within these stellar winds might act like cosmic mirrors, bouncing signals back and forth before they finally escape toward Earth. But even this idea struggles to account for the sheer scale of the delays observed. Then there's the wild card: plasma lensing. Unlike dust or gas, ionized plasma, superheated, electrically charged gas, can interact with radio waves in complex ways. If regions of this plasma drift between us and NML Cygni, they might refract the signals, creating multiple delayed versions. It's akin to how a mirage distorts light on a hot road, but in this case, the mirage is made of million-degree gas stretching across light years. The implications of these echoes go beyond one star. If NML Cygni's delayed signals stem from some unknown interstellar phenomenon, it could mean our maps of the galaxy's hidden structures are incomplete. Maybe there are invisible filaments of dark matter or rogue black holes warping space in ways we've yet to detect. Or perhaps the star itself is doing something we don't fully understand, pulsing in a way that creates artificial-seeming echoes. For now, NML Cygni keeps its secrets locked in those lingering radio whispers. But each echo is a clue, a piece of a puzzle that could reshape how we see the universe's invisible scaffolding. And that's the beauty of cosmic mysteries. They don't just defy expectations, they invite us to rethink them entirely. Now, shifting our gaze to another cosmic enigma, we encounter the bewildering behavior of VY Canis, a hypergiant so immense it defies comprehension. If placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. Yet, it's not just its staggering size that baffles astronomers. It's the star's erratic radio signals, which flicker and shift like a candle in a storm. VY Canis emits radio waves that don't just fluctuate, they leap across frequencies with no discernible pattern. One moment, they're a steady hum in the lower bands, the next they've jumped to piercing highs, only to drop again seconds later. This isn't the gentle ebb and flow of typical stellar activity. It's as if the star's very heartbeat is chaotic, leaving researchers scrambling for explanations. So what could be causing this cosmic static? One camp points to the star's internal chaos. Hypergiants like VY Canis are seething cauldrons of plasma with convection currents larger than entire solar systems. These turbulent motions could generate shifting magnetic fields, which in turn might twist and fracture the radio emissions, creating the erratic signals we detect. Imagine a pot of water boiling violently. The bubbles rise unpredictably, just as VY Canis' radio waves might surge and fade with its internal churn. But there's a twist. Some of these frequency shifts are so abrupt that internal turbulence alone struggles to explain them. Could an unseen cosmic neighbor be tugging at VY Canis' emissions? Rogue planets, though rare around hypergiants, aren't impossible. A massive, wandering world or even a stray black hole could orbit the star, its gravity warping the radio waves as they travel toward us. Picture a ship sailing through choppy waters, its course altered by hidden currents. If such an object lurks near VY Canis, its influence might be imprinting these bizarre shifts onto the star's signals. Then there's the magnetar hypothesis. Some hypergiants in their death throes may birth magnetar's neutron stars with unimaginably strong magnetic fields. If VY Canis harbors one nearby, its field could be slicing through the hypergiant's own emissions, scrambling them into the erratic patterns we observe. It's like holding a magnet near a radio. Suddenly, the signal crackles and distorts in ways you'd never expect. Yet, every theory has its flaws. No rogue planet or black hole has been spotted near VY Canis, and magnetars leave other telltale signs that haven't been detected. This leaves astronomers pondering whether we're missing a piece of the puzzle, perhaps an entirely new stellar phenomenon. What makes VY Canis' frequency shifts so tantalizing is their potential to reveal hidden forces at work in the universe. If the cause is internal, it could rewrite our models of hypergiant dynamics. If external, it might hint at invisible objects lurking in the cosmic dark. For now, the star's radio outbursts remain a cipher, each erratic pulse a whisper of mysteries yet to be decoded. And in that uncertainty lies the thrill of discovery, the chance that the next observation might finally crack the case. Now, let's turn our attention to the enigmatic Rho Cassiopeiae, a yellow hypergiant that refuses to play by the rules. Unlike the chaotic radio waves of VY Canis, Rho Cassiopeiae delivers something even more startling: sporadic, high-energy bursts that defy expectations. These aren't your ordinary stellar flares. They're violent eruptions of energy, intense enough to rival the precursors of supernova, yet they come and go without the star meeting its fiery end. Rho Cassiopeiae sits roughly 10,000 light-years away, a luminous beacon in the night sky. Yellow hypergiants like this one are rare, perched on the edge of instability, and Rho Cassiopeiae is no exception. Normally, stars of this type exhibit gradual, predictable changes as they inch toward their final explosions. But Rho Cassiopeiae, it sends out sudden, blinding bursts of energy without warning, as if teasing astronomers with glimpses of a catastrophe that never arrives. What makes these bursts so baffling is how they differ from typical supernova precursors. Most massive stars on the brink of collapse emit a steady buildup of radiation, their outer layers growing unstable before the final detonation. Rho Cassiopeiae, however, behaves like a cosmic firecracker, flaring up dramatically before settling back into an eerie calm. These aren't the death throes of a star. They're something else entirely. One leading theory suggests that the star's outer layers might be experiencing violent convulsions, throwing off massive shells of material in fits and starts. Imagine a pot of water boiling over, but instead of a steady simmer, it erupts in sudden, explosive geysers. That's the kind of erratic behavior Rho Cassiopeiae seems to exhibit. These outbursts could stem from deep within the star's unstable core, where nuclear reactions flicker unpredictably, sending shockwaves through its atmosphere. But there's another twist. Some astronomers speculate these bursts could be tied to the star's rare and poorly understood evolutionary phase. Yellow hypergiants occupy a brief, turbulent stage between being red supergiants and Wolf-Rayet stars, and Rho Cassiopeiae might be caught in the middle of this transformation. Its outbursts could be the result of internal struggles, violent adjustments as it sheds layers and reconfigures itself. It's like watching a star rewrite its own rulebook in real time. The most perplexing part, these bursts don't fit neatly into any known stellar models. If they were supernova precursors, we'd expect them to grow more frequent and intense until the star finally explodes. Instead, Rho Cassiopeiae flares up and then retreats, leaving astronomers scratching their heads. Could these outbursts be the sign of some entirely new stellar phenomenon? Or are we witnessing the star's desperate attempts to stabilize itself against forces we don't yet understand? Rho Cassiopeiae's mystery serves as a humbling reminder of how much we still have to learn about the lives of hypergiants. Every burst it sends our way is a challenge, a call to rethink what we know about stellar evolution. For now, it remains one of space's most captivating enigmas, a star that refuses to be easily defined. And as long as it keeps surprising us, astronomers will keep watching, waiting for the next clue that might finally unlock its secrets. Now, let's shift our gaze to one of the most extreme stars in our galaxy, the Pistol Star. Nestled near the center of the Milky Way, this luminous hypergiant is already a spectacle. But what truly baffles astronomers isn't just its staggering brightness. It's the eerie, ultra-low-frequency pulses it emits, whispers of energy so faint they almost slip past our detectors, yet persistent enough to demand an explanation. The Pistol Star, named for the pistol-shaped nebula it illuminates, is a beast of a star, somewhere between 80 and 150 times the mass of our Sun. It's a star that shouldn't exist according to some models, yet there it is, blasting out radiation and stellar winds with unimaginable force. But hidden beneath all that fury are these peculiar pulses, rhythmic and quiet, like a heartbeat in a thunderstorm. Unlike the violent eruptions of Rho Cassiopeiae or the erratic radio shifts of VY Canis, these pulses are subtle. They occur at frequencies so low that they stretch the limits of our detection capabilities. Imagine trying to hear a whisper in a crowded room. That's the challenge astronomers face when studying these signals. What's even stranger is that they don't match any known stellar activity. Typical pulsations from massive stars come from surface oscillations or internal pressure waves, but the Pistol Star's pulses don't fit those patterns. There's something else entirely. So what could be causing them? One compelling theory points to magnetar-like activity. Magnetars are neutron stars with unimaginably strong magnetic fields, and they're known to emit similar low-frequency pulses. But the Pistol Star isn't a neutron star, it's a hypergiant. Could it have a magnetic field so intense that it mimics a magnetar's behavior? Some researchers think so. If true, this would force us to rewrite our understanding of how magnetic fields behave in hypergiants, suggesting these stars might harbor forces far more extreme than we've ever imagined. Then there's the possibility of exotic matter interactions. Deep in the Pistol Star's core, where temperatures and pressures defy comprehension, matter might exist in states we've never observed. Quark-gluon plasma, strange matter, or other theoretical substances could be generating these pulses as they shift and churn inside the star. It's a wild idea, but when dealing with a star this extreme, wild ideas often lead to breakthroughs. But here's the real puzzle: these pulses aren't constant. They come and go, sometimes vanishing for long stretches before reappearing without warning. This inconsistency makes them even harder to study. Are they tied to the star's turbulent mass loss, where it's shedding entire solar masses in violent outbursts? Or do they stem from hidden companions, an unseen neutron star or black hole tugging at the Pistol Star's fabric? For now, the Pistol Star keeps its secrets close. Its silent pulses are a cosmic riddle, a reminder that even the most luminous objects in the universe can hide the most subtle mysteries. And as long as it keeps whispering, astronomers will keep listening, hoping to decode the message hidden in those faint, enigmatic beats. Up next, another hypergiant defies expectations with magnetic fields so intense they bend the laws of physics. But that's a story for another signal. Now, let's turn our attention to a celestial oddity that's rewriting the rules of stellar magnetism IRC plus 10,420. This hypergiant, shrouded in its own expelled gases, isn't just massive or luminous, it's bending light in ways that shouldn't be possible, revealing magnetic forces so intense they've left astrophysicists stunned. Imagine light as a wave vibrating in all directions as it travels through space. But when light becomes polarized, those vibrations align in a single plane, like ocean waves rolling uniformly toward shore. This usually happens when light passes through a magnetic field, which acts like a cosmic comb, straightening its chaotic vibrations. Now, here's where IRC plus 10,420 throws a wrench into the works. The light we detect from this star isn't just slightly polarized, it's twisted into patterns so extreme they suggest magnetic fields orders of magnitude stronger than anything our models predict for a hypergiant. What makes this even stranger is the star's life stage. IRC plus 10,420 is what astronomers call a post-red supergiant, a transitional phase where the star has already ballooned to colossal size and is now contracting, shedding layers of its atmosphere in violent outbursts. Normally, stars like this have turbulent but relatively disorganized magnetic fields. Yet, the polarization signals from IRC plus 10,420 reveal something shockingly structured, almost geometric, as if the star's magnetism has been braided or wound into tight coils. So, what could possibly create such intense, ordered magnetism in a star like this? One leading theory points to dynamo effects gone wild. Inside stars, churning plasma generates magnetic fields, much like Earth's molten core creates our planet's magnetism. But in a hypergiant where convection is chaotic and extreme, dynamos were thought to produce messy, unstable fields. Yet, IRC plus 10,420's data suggests the opposite, a magnetic field so coherent it defies expectations. Could rapid rotation be the key? If the star is spinning faster than we've measured, it might be winding its magnetic field into these bizarre, polarized configurations. Then there's the darker, more speculative possibility, a hidden stellar corpse. Some researchers wonder if a neutron star or white dwarf, the dense remnant of a former companion, might lurk nearby, its own fierce magnetism interacting with the hypergiant's outer layers. Such a partnership could amplify and structure IRC plus 10,420's magnetic field in ways we've never seen. But here's the twist: polarization isn't constant. It fluctuates over time, as if the star's magnetic field is alive, twisting and reorganizing itself. This volatility makes it even harder to pin down a cause. Is the star's turbulent mass loss distorting its own magnetism? Or are we witnessing the birth of something entirely new, a magnetic phenomenon unique to hypergiants in this rare evolutionary phase? One thing's certain: IRC plus 10,420 is forcing us to rethink how magnetism operates in the most extreme stars. Its polarized whispers are a cosmic puzzle, a reminder that even the most well-studied laws of physics can bend under the weight of a hypergiant's fury. Up next, we'll encounter a star whose radio emissions sound almost musical, harmonized in ways that blur the line between nature and something far more mysterious. Now, let's journey to a star that seems to be singing its own cosmic tune, VY Sagittarii. Nestled in the constellation Sagittarius, this hypergiant isn't just emitting random noise. Instead, it's broadcasting harmonic radio patterns so precise they almost sound engineered, like a celestial symphony playing on repeat. But don't let that fool you. This isn't some interstellar radio station. It's a natural phenomenon that's shaking up our understanding of how stars behave. So, what exactly are we hearing? The signals from VX Sagittarii aren't the usual chaotic bursts or static hisses we expect from massive stars. Instead, they're rhythmic, repeating patterns that resemble harmonics. Think of the way a plucked guitar string vibrates at specific frequencies, creating overtones. In VX Sagittarii's case, these radio harmonics follow a mathematical order, almost like a musical scale. The star's outer layers seem to be resonating in a way that produces these eerily structured emissions. But here's where things get even stranger. Current stellar acoustic models, the theories that explain how sound waves travel through stars, can't fully account for these harmonics. In most stars, sound waves generated by turbulent convection bounce around internally, creating vibrations that match the star's natural frequencies. But VX Sagittarii's harmonics are far more complex and organized than these models predict. It's as if the star has an additional layer of physics at play, something we haven't yet plugged into our equations. One leading hypothesis suggests that VX Sagittarii's immense size and instability might be key. As one of the largest known stars, its outer layers are incredibly diffuse, almost like a loosely held atmosphere. When material is ejected or collapses back onto the star, it could create shock waves that resonate in unexpected ways, amplifying certain frequencies into these harmonic patterns. Imagine sloshing water in a giant bowl. The ripples interact, sometimes reinforcing each other to create standing waves. VX Sagittarii might be doing something similar, but on a cosmic scale. Another possibility involves magnetic fields. While IRC plus 10,420 stunned us with its polarized magnetism, VX Sagittarii's harmonics might also be shaped by invisible magnetic structures. If the star's magnetic fields are twisted or looped in just the right way, they could act like cosmic tuning forks, forcing the radio emissions into these precise harmonic intervals. But here's the million-dollar question: could these signals ever hint at something artificial? The short answer is almost certainly no. While the harmonics are undeniably strange, they still fit within the realm of natural astrophysics, just pushed to their extreme limits. However, that doesn't make them any less fascinating. In fact, VX Sagittarii's emissions are teaching us that hypergiants might have acoustic behaviors we never imagined, behaviors that could rewrite how we model stellar interiors. What makes this star particularly compelling is its variability. The harmonics aren't static, they shift over time, sometimes becoming more pronounced, other times fading into the background. This suggests that whatever process is generating them is dynamic, reacting to changes in the star's atmosphere or magnetic environment. It's a reminder that hypergiants like VX Sagittarii aren't just massive, they are also incredibly volatile, with layers of complexity we're only beginning to decode. Up next, we'll meet a star whose heartbeat, like pulses, defy everything we know about stellar rhythms. But for now, VX Sagittarii stands as a testament to the universe's ability to surprise us, proving that even the most natural phenomena can sometimes feel almost too perfect to be real. Now let's turn our attention to a star that pulses with a rhythm unlike any other Mu Cephei. Known as the Garnet Star for its deep red hue, this hypergiant isn't just visually striking. It's emitting something even more intriguing, a steady, heartbeat-like signal that defies everything we know about stellar pulsations. At first glance, Mu Cephei's rhythmic pulses might seem similar to the natural vibrations seen in other variable stars. But dig a little deeper and the story gets far more mysterious. Most pulsating stars expand and contract in predictable cycles, driven by internal processes like nuclear fusion or convection. Mu Cephei, however, beats with a precision that doesn't align with any known stellar models. It's as if the star has its own hidden metronome, ticking away with a regularity that astronomers can't yet explain. So what's behind this cosmic heartbeat? One leading theory points to undiscovered layers deep within the star. Mu Cephei's enormous size, over 1,000 times the radius of our Sun, means its internal structure is incredibly complex. Current models struggle to account for the sheer scale of its convection zones, where heat and material circulate in massive currents. Some researchers speculate that hidden boundaries or density variations inside the star could be creating resonant cavities, amplifying certain vibrations into these rhythmic pulses. Imagine tapping a glass filled with water at different levels, each produces a distinct tone. Mu Cephei might be doing something similar, but with shock waves rippling through its gaseous layers. But there's another twist. External forces could also be at play. Mu Cephei isn't alone in its corner of space. It's part of a binary system orbiting alongside a smaller companion star. While the companion isn't close enough to directly distort Mu Cephei's shape, its gravitational tug could still be influencing the hypergiant's behavior. Subtle tidal forces might be nudging the star's outer layers, triggering these rhythmic emissions in ways we haven't yet modeled. Alternatively, debris or dust in the system could be interacting with Mu Cephei's intense stellar winds, creating pressure waves that mimic a heartbeat. What makes this signal particularly puzzling is its consistency. Unlike the chaotic bursts from stars like Rho Cassiopeiae or the shifting harmonics of VX Sagittarii, Mu Cephei's pulses are remarkably stable over time. This rules out short-term phenomena like magnetic flares or random ejections. Instead, the star seems locked in a long-term pattern, hinting at a process that's deeply ingrained in its structure or environment. Could this be evidence of entirely new physics? Probably not, but it's a stark reminder of how much we still don't understand about hypergiants. Mu Cephei's heartbeat challenges the assumption that all stellar pulsations follow the same rules. It suggests that stars of this size and age might harbor unique mechanisms, whether internal or external, that we've yet to uncover. For now, Mu Cephei keeps its secrets close, pulsing steadily like a cosmic drum in the darkness. But each beat is a clue, urging us to listen more closely to the hidden rhythms of the universe. Next up, we'll encounter a star that defies another expectation, RW Cephei, where X-ray flares erupt from a surface that should be far too cool to produce them. But one thing's certain, the deeper we look, the more these giants remind us that the universe thrives on the unexpected. Now, let's venture into a paradox hidden in the cosmos. RW Cephei, a star that seems to break its own rules. This hypergiant, glowing with a relatively cool surface temperature, should be the last place we'd expect to find violent X-ray flares. Yet, astronomers have detected exactly that. Bursts of high-energy radiation erupting from a star that, by all accounts, shouldn't be capable of producing them. It's like finding a glacier spouting flames. At first, the discovery seemed impossible. RW Cephei is a red supergiant, a class of stars known for their expansive, low-temperature atmospheres. Their surfaces hover around 3,500 Kelvin, far cooler than stars like our Sun, which regularly emit X-rays through coronal activity. For a star like RW Cephei, the energy required to generate X-rays simply shouldn't exist in its outer layers. So where are these flares coming from? One compelling theory points to hidden hotspots lurking beneath the star's seemingly tranquil exterior. Imagine RW Cephei as a simmering pot with occasional, furious bubbles breaking the surface. Turbulence deep within its convection zones could create localized regions of intense heat where temperatures spike enough to produce X-rays. These pockets might be driven by magnetic reconnection, the same process that triggers solar flares on our Sun, but on a scale we've never witnessed before. If RW Cephei's magnetic field is tangled and chaotic, it could snap and release enormous energy in bursts, piercing through the cooler outer layers like a flare gun in fog. But there's another, even more exotic possibility, an accretion disk. RW Cephei isn't solitary, it's part of a binary system. While its companion star hasn't been directly observed, gravitational interactions suggest it's there. If this companion is a compact object, like a neutron star or even a black hole, material stripped from RW Cephei could spiral inward, forming a disk of superheated gas. As this gas accelerates and collides, it would emit X-rays, creating the flares we detect. It's a cosmic robbery, with the hypergiant's outer layers being siphoned away, generating violence in the process. What's especially puzzling is the irregular timing of these flares. Unlike Mu Cephei's steady heartbeat, RW Cephei's X-ray bursts are sporadic and unpredictable. Some researchers suggest this points to a combination of mechanisms, perhaps both magnetic hotspots and accretion disk activity alternating in dominance. It's a reminder that hypergiants are anything but uniform. Their sheer size and complexity allow for multiple, overlapping phenomena. The discovery of these flares forces us to rethink the boundaries of stellar physics. RW Cephei defies the neat categories we've created, proving that even the coolest giants can harbor extremes. Whether it's hidden magnetic fury or the gravitational grip of an unseen companion, one thing is clear: this star is far more than its placid exterior suggests. Up next, we'll shift our gaze to KY Cygni, where infrared signals flicker with patterns no one can quite decipher. But if there's a lesson from RW Cephei, it's that the universe loves to hide its most explosive secrets in plain sight. Now, let's turn our attention to another cosmic oddity, KY Cygni, a hypergiant star that refuses to play by the rules. Unlike the predictable rhythms of most stars, KY Cygni emits infrared signals that flicker and dance in ways astronomers can't fully explain. These erratic fluctuations are more than just random noise. They hint at processes we're only beginning to understand, hidden beneath the star's fiery surface. At first glance, KY Cygni seems like a typical red hypergiant, massive, luminous, and swaddled in vast clouds of dust. But when researchers trained infrared telescopes on it, they noticed something peculiar. The star's infrared emissions didn't follow the steady, predictable patterns seen in other hypergiants. Instead, they spiked and dipped unpredictably, as if someone were turning a cosmic dimmer switch on and off at random. This behavior is especially puzzling because infrared light typically comes from heat radiating off dust or gas, which should be relatively stable around a star of this size. One leading theory blames the erratic signals on dense, shifting dust clouds surrounding KY Cygni. Hypergiants like this one are notorious for shedding enormous amounts of material, creating thick shrouds of dust that orbit the star. If these clouds are clumpy or unevenly distributed, they could block infrared light in unpredictable ways, causing the chaotic fluctuations we observe. Think of it like walking past a flickering street lamp obscured by blowing smoke. Sometimes the light shines through clearly, other times it's muffled or distorted. But there's a twist. Some scientists argue that dust alone can't explain the extreme variability of KY Cygni's signals. The fluctuations are too rapid, too irregular. This has led to a far more exotic hypothesis: quantum vacuum effects. In the intense gravitational and electromagnetic environment near a hypergiant, the very fabric of space-time might behave strangely. Quantum fluctuations, tiny, spontaneous bursts of energy in the vacuum of space, could interact with the star's radiation, amplifying or scattering infrared light in unpredictable ways. It's a wild idea, but in the extreme conditions around KY Cygni, even the rules of quantum physics might bend. Adding to the mystery is the star's sheer size. KY Cygni is so enormous that if it replaced our Sun, its outer layers would extend past Jupiter's orbit. At that scale, even tiny instabilities can create colossal effects. Turbulence in its outer atmosphere or powerful magnetic fields twisting beneath the surface could be stirring up the dust and gas in ways we can't yet model. What makes KY Cygni especially fascinating is that it challenges our assumptions about how stars behave at the most fundamental level. Most stellar models assume a degree of symmetry and regularity, but this hypergiant throws that out the window. Whether it's dust playing tricks on us or something deeper lurking in the quantum realm, one thing is certain: KY Cygni isn't just breaking the mold, it's rewriting the rules entirely. Up next, we'll examine H Scorpii, a star that's gone eerily quiet after years of activity. If VY Cygni teaches us anything, it's that the universe's most baffling secrets often lie in the details we least expect. Now, let's shift gears to something just as puzzling, but in a completely different way. H Scorpii, a hypergiant star that's suddenly gone silent. After decades of broadcasting strong radio emissions, this star has abruptly stopped transmitting, leaving astronomers scratching their heads. It's like a radio station that's been playing non-stop for years suddenly going off the air without warning. The question is why H Scorpii isn't just any star. It's a red hypergiant, one of the largest and most luminous stars in our galaxy, with a history of violent outbursts and dramatic mass loss. For years, it emitted steady radio waves, a common trait for stars of its kind, as their turbulent atmospheres and expanding gas shells interact with magnetic fields. But then, the signal stopped. No gradual fade, no last burst, just silence. This kind of sudden shutdown isn't just unusual, it's unprecedented in our observations of hypergiants. One possibility is that AH Scorpii is on the verge of a catastrophic collapse. Stars like this are ticking time bombs, destined to end their lives as supernova. If the star's core is nearing the point of collapse, the outer layers might be reacting in ways that shut down radio emissions before the final explosion. Think of it like a car engine sputtering out before it stalls. The star's internal processes could be faltering, cutting off the mechanisms that generate radio waves. If that's the case, we could be witnessing the calm before the cosmic storm. A fleeting quiet before H Scorpii unleashes one of the most energetic events in the universe. But there's another, less dramatic explanation, an observational blind spot. The universe is vast, and sometimes our instruments simply miss things. Dust clouds or interference from interstellar material could be blocking our view, creating the illusion of silence when the star is still active. It wouldn't be the first time cosmic clutter has played tricks on us. Even with our most advanced telescopes, space has a way of keeping its secrets hidden just out of sight. What makes this mystery even more intriguing is that AH Scorpii isn't behaving like other stars on the brink of collapse. Typically, hypergiants show clear warning signs, brightening, rapid pulsations, or erratic ejections of material before they go silent. But AH Scorpii's radio emissions cut off without any of these precursors. That absence of warning flags has led some researchers to wonder if we're missing a key piece of the puzzle, something about hypergiant physics we haven't yet uncovered. Could this silence be a clue to an entirely new stellar phenomenon? Or is it just a cosmic illusion, a temporary obstruction in our line of sight? Either way, H Scorpii's sudden quiet is a stark reminder of how much we still have to learn about these colossal stars. Up next, we'll take a closer look at S Perseus and its strange, clustered radio echoes, another mystery that challenges our understanding of how hypergiants shape their surroundings. One thing's for sure, the universe has no shortage of surprises. Now, let's turn our attention to another cosmic enigma, S Perseus, a hypergiant star that's sending us radio echoes in clusters, almost as if it's whispering secrets through space. Unlike the sudden silence of H Scorpii, S Perseus is anything but quiet. Instead, it's producing radio signals that bounce back in strange, repeating patterns, hinting at something unusual lurking in its surroundings. S Perseus, a massive red hypergiant located in the constellation Perseus, has long fascinated astronomers with its sheer size and volatile behavior. But what's really caught their attention recently are these clustered radio echo signals that don't arrive in a smooth, steady stream but instead come in tight, repetitive bursts. It's like hearing an echo in a canyon, but instead of fading evenly, the sound bounces back in sharp, unexpected pulses. This isn't normal for a star like S Perseus, and it's got scientists scrambling for explanations. One leading theory is that these echoes are caused by dense debris rings or shells of material orbiting the star. Hypergiants are notorious for shedding colossal amounts of gas and dust as they near the end of their lives, and S. Perseus is no exception. If this material isn't ejected evenly but instead forms clumps or arcs around the star, it could create the perfect conditions for clustered echoes. Imagine throwing a pebble into a pond with scattered rocks. The ripples wouldn't spread smoothly but would bounce back irregularly, just like the radio signals we're detecting. Another possibility is that shock waves from violent stellar activity are shaping these echoes. Hypergiants like S. Perseus experience extreme eruptions, ejecting material at incredible speeds. When these ejections collide with slower-moving gas or dust clouds, they generate shock waves that can distort and amplify radio emissions. The result: signals that arrive in clusters rather than a continuous stream. It's like listening to a fireworks display. Each burst is distinct, triggered by a separate explosion or collision. What makes this even more intriguing is that these echoes aren't random. They appear to follow a semi-regular pattern, almost as if something out there is organizing them. That's led some researchers to speculate about unseen companions, perhaps a smaller star or even a black hole, perturbing S. Perseus's surroundings and creating these structured reflections. While there's no direct evidence yet, the idea of a hidden gravitational influence shaping these echoes adds another layer of mystery to the story. But here's the twist: our current models of hypergiant stars don't fully account for this kind of behavior. If S. Perseus is surrounded by debris rings or shock waves, they'd have to be far more complex than anything we've observed around similar stars. That raises a bigger question: are we seeing a rare, short-lived phase in a hypergiant's life? Or is there a fundamental gap in our understanding of how these colossal stars interact with their environments? The echoes from S. Perseus aren't just cosmic noise, they're clues. Each clustered signal holds information about the star's surroundings, its history, and possibly its future. Studying them could help us unravel not just this one mystery, but also broader questions about how hypergiants evolve and ultimately meet their end. Coming up, we'll explore WOHG 64 and its baffling light curves, another celestial puzzle where the star's behavior defies expectations. From radio echoes to erratic brightness, these hypergiants keep proving that the universe is far stranger than we ever imagined. Turning our gaze deeper into the cosmos, we encounter WOHG 64, a hypergiant whose flickering light tells a story as puzzling as the echoes of S. Perseus. This colossal star, nestled in the Large Magellanic Cloud, isn't just dimming and brightening at random, it's doing so in ways that defy every model astronomers have thrown at it. And if the erratic light wasn't baffling enough, WOHG 64 throws in another twist: strange, crackling radio noise that seems to dance in time with its brightness changes. What's going on here? WOHG 64 is one of the largest known stars, a red hypergiant so immense that if placed in our solar system, its surface would swallow Saturn's orbit. Stars this size are expected to be unstable, but WOHG 64 takes unpredictability to another level. Its light curve, the graph tracking its brightness over time, looks less like a smooth wave and more like a frantic heartbeat, spiking and plunging without clear rhythm. Normally, such variations could be explained by pulsations or surface eruptions, but here's the kicker: the changes don't match any known stellar behavior. They're too sharp, too frequent, and most intriguingly, they're accompanied by bursts of radiostatic that shouldn't exist in a star this cool. So what could be causing this cosmic tantrum? One compelling theory points to extreme mass loss events. Hypergiants are notorious for shedding their outer layers in violent outbursts, and WOHG 64 is no exception. Observations suggest it's cloaked in a thick shroud of dust, likely ejected during prior eruptions. But here's where it gets weird: the dust isn't evenly distributed. Instead, it seems to clump into dense clouds that sporadically block the star's light from our view, creating those jagged dips in brightness. Meanwhile, the radio noise could stem from charged particles accelerated by shock waves as ejected material slams into slower-moving gas. Think of it like a stellar thunderstorm. Every time a massive cloud of plasma breaks free, it generates turbulent electromagnetic crackles we pick up as radio bursts. Another possibility, magnetic reconnection. While red hypergiants aren't typically magnetic powerhouses like smaller stars, WHG64's sheer size might allow for tangled magnetic fields in its outer layers. If these fields suddenly snap and reorganize, a process called reconnection, they could unleash colossal energy, heating localized patches of the star's atmosphere and triggering both brightness spikes and radio emissions. It's akin to solar flares on our sun, but scaled up to hypergiant proportions, with enough force to momentarily outshine entire sections of the star. Yet neither theory fully explains the patterns. The light curve's irregularity suggests something more chaotic than orderly magnetic events or predictable ejections. Some researchers speculate that WHG64 might be interacting with an unseen companion, a smaller star or even a black hole, whose gravitational tugs distort the hypergiant's outer layers, stirring up turbulence and triggering erratic outbursts. Others wonder if we're witnessing the early stages of a rare evolutionary phase, where the star's core is preparing for a supernova while its outer envelope writhes in instability. The enigma of WHG64 reminds us that even the most massive stars guard secrets. Its erratic light and radio whispers challenge our assumptions about how hypergiants behave in their final epochs. Up next, we'll shift focus to V766 Centauri, where the signals take an even stranger turn, brief, bird-like chirps that defy all expectations of stellar acoustics. The universe, it seems, has a flair for the unexpected. Now let's zoom in on V766 Centauri, where the cosmos throws us yet another curveball, this time in the form of sounds that wouldn't be out of place in a forest at dawn. Unlike the rumbling static of WHG64, the signals here are sharp, fleeting, and eerily reminiscent of bird chirps. Imagine tuning a radio telescope and catching whispers from a star that sound less like a celestial body and more like a songbird. That's exactly what astronomers observed with V766 Centauri, a yellow hypergiant whose bizarre acoustic signature has left experts scratching their heads. At first glance, these chirps seem impossible. Stars aren't supposed to produce such crisp, staccato noises, especially not hypergiants, which typically emit low-frequency rumbles or sustained radio waves. Yet V766 Centauri defies expectations with bursts lasting mere milliseconds, each one a rapid uptick in frequency followed by silence. The patterns are so distinct that initial suspicions lean toward instrumental glitches or even interference from Earth-based sources. But repeated observations confirmed the chirps were real and undeniably tied to the star. So what's creating these celestial tweets? One leading explanation points to plasma oscillations deep within V766 Centauri's atmosphere. Hypergiants like this one are cauldrons of superheated plasma, where charged particles swirl in turbulent currents. Under the right conditions, pockets of plasma can vibrate at specific frequencies, much like air in a wind instrument. If these oscillations become unstable, say, due to abrupt magnetic shifts or shock waves from convection, they might produce brief, high-pitched bursts detectable as radio chirps. Think of it as the star plucking its own magnetic strings, creating sonic sparks that zip through space. Then there's the wildcard theory, maser amplification. In rare cosmic environments, molecules like water or silicon monoxide can act as natural lasers, amplifying specific radio frequencies into intense beams. V766 Centauri's dense, molecule-rich outer layers could be hosting such masers, with turbulent stellar winds triggering sporadic bursts. These wouldn't sound like typical stellar noise because masers emit narrow-frequency signals, akin to a whistle cutting through white noise. Still, even this doesn't fully account for the chirp's irregular timing or their uncanny resemblance to biological sounds. Could the answer lie beyond natural astrophysics? While it's tempting to entertain exotic possibilities, alien beacons or engineered signals, the absence of repeating patterns or encoded information makes technosignatures unlikely. Instead, the most plausible scenarios involve extreme stellar physics we've yet to map. For instance, V766 Centauri might harbor a hidden companion, a smaller star or neutron star, whose gravity stirs up plasma tsunamis on the hypergiant surface. Each collision could generate shock waves that manifest as those fleeting chirps. Alternatively, the star's own rotation might be warping its magnetic field lines, creating sporadic snaps of energy as they reconfigure. The mystery of these chirps underscores how much we still don't understand about hypergiant behavior. V766 Centauri's avian mimicry challenges our models of stellar acoustics, proving that even the loudest voices in the cosmos can still surprise us with their whispers. Up next, we'll turn our attention to HD 179821, where the signals take on an entirely different character, sweeping frequency patterns that eerily resemble man-made radar, yet arise from purely natural processes. The universe, it seems, has a penchant for blurring the line between the familiar and the inexplicable. Now let's shift our gaze to HD 179821, where the cosmos serves up a signal so uncanny it could easily be mistaken for something human-made. This hypergiant doesn't chirp or hum, it sweeps, sending out radio waves that glide up and down the frequency spectrum like a radar scanner. It's as if the star is tuning an invisible dial, cycling through cosmic stations with eerie precision. What makes these sweeps so baffling is their resemblance to technology we've built right here on Earth. Yet, HD 179821 is a natural phenomenon, proving once again that the universe has its own way of mirroring the familiar in the most unexpected places. So how does a star produce signals that mimic our own machinery? The answer likely lies in the chaos of its stellar winds. Hypergiants like HD 179821 are notorious for their ferocious mass loss, ejecting gas and dust at speeds that can reach hundreds of kilometers per second. These winds don't blow uniformly, they spiral, collide, and create shock waves as they interact with the star's magnetic field. Picture a hurricane twisting through an obstacle course, its gusts carving out patterns in the surrounding space. Now imagine those turbulent winds loaded with charged particles, each one acting like a tiny radio transmitter. As they accelerate and decelerate, their emissions shift in frequency, creating the sweeping effect we detect. But there's a twist. Unlike human radar, which follows a predictable mechanical rhythm, HD 179821 sweeps are irregular. Sometimes they're slow and drawn out, like the drawn breath of a singer holding a note. Other times they're rapid and disjointed, as if the star can't decide where to land on the dial. This inconsistency rules out simple rotation or pulsation as the sole cause. Instead, astronomers suspect the star's winds are clumping, forming dense pockets of material that act like prisms, bending and scattering radio waves in unexpected ways. These clumps might arise from instabilities in the wind itself, or from the gravitational tug of an unseen companion stirring the pot. Another piece of the puzzle involves maser activity, much like we saw with V766 Centauri. HD 179821 outer layers are rich in molecules like water and silicon monoxide, which can amplify specific frequencies into intense beams. As the stellar winds buffet these molecules, they could generate sweeping maser signals that drift across the radio spectrum. It's a bit like shining a flashlight through a spinning disco ball. The beam jumps erratically, creating fleeting patterns of light. In this case, the light is radio waves, and the disco ball is a hypergiant's turbulent atmosphere. Of course, no discussion of strange signals would be complete without addressing the elephant in the room. Could this be something more deliberate? The resemblance to radar is undeniably striking, but there's no evidence of encoded information or repeating sequences that would hint at artificial origins. Nature, it seems, is simply a master of mimicry. What's far more fascinating is what these sweeps reveal about the inner workings of hypergiants. HD 179,821, erratic behavior suggests a level of complexity in stellar winds that our current models can't fully capture. Are there hidden magnetic structures guiding these winds? Could there be pockets of extreme turbulence we've yet to observe? One thing's certain, HD 179,821 frequency sweeps are a reminder that even the most advanced stars still hold onto their secrets. Up next, we'll delve into an even stranger mystery near RSGC 1F01, where signals hint at a cosmic illusion, a microlensing event with no visible lens. The universe, it seems, loves a good magic trick. Now let's turn our attention to a cosmic sleight of hand near RSGC 1F01, where the universe seems to be playing tricks on us. Here, astronomers have detected signals that strongly suggest a microlensing event, a phenomenon where the gravity of a foreground object bends and magnifies light from a star behind it, acting like a natural telescope. But there's a catch. In this case, there's no visible lens. It's as if the cosmos is winking at us, showing off an illusion with no explanation. So, what exactly is going on? Microlensing typically happens when a compact object like a star, planet, or even a black hole passes directly between us and a distant star. The foreground object's gravity warps spacetime, bending the background star's light around it and creating a temporary brightening. These events are fleeting but predictable, often lasting days or weeks. Yet near RSGC 1F01, the signals match microlensing's fingerprint: sudden brightening, symmetrical light curves, but no lens can be found. No star, no planet, not even a faint whisper of an object in the data. It's like hearing footsteps in an empty room. This absence has led scientists down a fascinating rabbit hole of speculation. One compelling theory points to dark matter. Could this invisible substance, which makes up most of the universe's mass, be clumping into dense chunks that act as lenses? While dark matter doesn't interact with light, its gravitational pull certainly does. If tiny, invisible knots of it drift through space, they could theoretically bend light without ever revealing themselves. Another tantalizing possibility: primordial black holes. These hypothetical relics from the universe's earliest moments would be as small as asteroids but as massive as stars, making them perfect stealth lenses. But here's where things get even stranger. RSGC 1F01 isn't just any hypergiant, it's part of a star cluster teeming with massive, luminous stars. The environment is chaotic, with stellar winds and radiation fields that could obscure a faint lens. Yet, even after scouring the region with infrared and radio telescopes, astronomers have found no trace of a culprit. Some have even proposed that the lens itself might have moved out of alignment by the time follow-up observations began, like a magician vanishing before the audience spots the trick. The implications are profound. If dark matter or primordial black holes are responsible, it would revolutionize our understanding of these elusive entities. Dark matter's distribution is thought to be smooth on small scales, but microlensing events like this could hint at unexpected clumpiness. Primordial black holes, meanwhile, remain purely theoretical. Their detection would solve multiple cosmic mysteries at once. Of course, there's always the chance that the answer is something entirely unforeseen. Could it be a flaw in the data or an unknown stellar phenomenon mimicking microlensing? The beauty of RSGC 1F01's mystery is that it forces us to question even our most reliable tools. The universe, it seems, still has a few cards up its sleeve. Up next, we'll examine another head-scratcher, Stephenson 218, where a sudden emission spike vanished without a trace. Was it a glitch or something more? Stay tuned. Now let's shift our gaze to Stephenson 218, a star so colossal it makes most hypergiants look modest. Here, astronomers witnessed something bizarre, a sudden, unexplained spike in emissions that appeared and vanished in the blink of a cosmic eye. No gradual buildup, no lingering aftermath, just a single, defiant blip in the data that left scientists scrambling for answers. Was it a software hiccup, a fleeting cosmic event, or something even stranger? This stellar behemoth, one of the largest known stars in the universe, is no stranger to drama. Its sheer size means it's constantly shedding material and radiating immense energy. But what caught researchers off guard was the abruptness of this emission spike. Unlike typical stellar flares or eruptions, which leave traces, heated plasma, fading light curves, this event left no breadcrumbs. One moment, the data flared like a firework. The next, it was as if nothing had happened. The first challenge was ruling out the mundane. Could it have been an instrumental glitch? Telescopes and sensors are complex machines prone to the occasional electronic hiccup. Teams cross-checked data from multiple observatories, searching for matching signals. Some instruments saw it, others didn't. This inconsistency only deepened the mystery. If it wasn't the equipment, then what? One theory points to a phenomenon called magnetospheric transient events brief, violent releases of energy from a star's magnetic field. Imagine a rubber band stretched too tight, snapping suddenly. Stephenson 218's immense size and turbulent magnetic environment could, in theory, produce such a fleeting outburst. But here's the catch. These events usually leave some fingerprint, like X-ray afterglows or radio disturbances. This one left nothing. Another tantalizing idea involves stellar hiccups, internal disturbances where layers of the star collapse or rebound unexpectedly. In hypergiants, where material is constantly churning, a sudden shift in density or pressure might trigger a brief energy release. Yet even this doesn't fully explain the spike's clean disappearance. Normally, such disturbances ripple through a star's outer layers, creating observable waves. Here, the silence was deafening. Then there's the wild card. Could something have passed in front of the star? Not a microlensing event, but perhaps a dense cloud of dust or a rogue fragment of interstellar material, briefly magnifying the light before drifting away. It's a stretch, but in the absence of better explanations, even unlikely possibilities get a seat at the table. The implications are as puzzling as the event itself. If this was a real astrophysical occurrence, it challenges our models of hypergiant behavior. Stars this size aren't supposed to flicker like candle flames. But if it was a glitch, why did some instruments detect it? The universe, it seems, enjoys keeping us on our toes. Coming up, we'll explore HV 2112, where signals dance to a rhythm that's almost, but not quite, predictable. What cosmic conductor is orchestrating this near-perfect chaos? Stick around. Now, let's turn our attention to HV 2112, a hypergiant whose signals seem to follow a rhythm, but with a twist. This star's emissions aren't just irregular, they're almost regular, teasing astronomers with a pattern that never quite settles into predictability. It's like listening to a song where the beat keeps shifting ever so slightly, just enough to keep you guessing. HV 2112 sits in the Small Magellanic Cloud, a satellite galaxy of our Milky Way, and it's no ordinary star. Classified as a super-AGB star, a rare and short-lived phase of stellar evolution, it's already a cosmic oddball. But what really baffles scientists are the quasi-periodic signals it emits. Unlike the steady pulses of a pulsar or the predictable flares of a variable star, HV 2112 fluctuations are in a league of their own. They're close enough to periodic to suggest an underlying mechanism, yet just erratic enough to defy explanation. One leading theory points to chaotic dynamics within the star itself. Hypergiants like HV 2112 are tumultuous beasts with layers of plasma churning at different speeds and densities. Imagine a pot of water boiling violently. Some bubbles rise in near-perfect intervals while others burst unpredictably. Similarly, HV 2112 interior could be a maelstrom of convection currents and magnetic instabilities, generating signals that almost repeat but never quite align. Yet there's another intriguing possibility, an unseen companion. Binary systems are common in the cosmos, and a smaller star or even a black hole orbiting HV 2112 could be tugging on it gravitationally. This gravitational dance might distort the hypergiant's outer layers, creating quasi-periodic signals as material is pulled between the two objects. The slight irregularities could then stem from the companion's own orbit being slightly elliptical or influenced by other unseen forces. What makes HV 2112 particularly perplexing is the absence of direct evidence for a companion. If one exists, it's either too faint or too close to the hypergiant to detect with current telescopes. This leaves astronomers in a bind. Without concrete data, the binary hypothesis remains tantalizing but unproven. The implications stretch beyond HV 2112. If the signals stem from internal chaos, it could reshape our understanding of super-AGB stars and their role in cosmic evolution. If a hidden companion is the culprit, it would highlight how much we still don't know about the unseen partners of even the brightest stars. Either way, HV 2112 quasi-periodicity is a cosmic riddle waiting to be solved. Next, we'll tune into the eerie, machinery-like hum emanating from Betelgeuse J004444, 86 plus 412,804, 6. Is it the natural resonance of a hypergiant or something far more unexpected? Stay with us. Now let's shift our focus to something that sounds almost mechanical, an eerie, steady hum emanating from the hypergiant Betelgeuse J004444, 86 plus 412,804, 6. Unlike the erratic bursts or quasi-rhythms we've explored so far, this signal is a constant, low-frequency drone reminiscent of distant machinery. It's the kind of sound that makes you pause and wonder, could this be something more than just stellar activity? This hypergiant, nestled in the Triangulum Galaxy, has baffled astronomers with its persistent hum. At first glance, it aligns with what we know about natural stellar resonances. Massive stars often vibrate like colossal bells, producing low-frequency waves as their surfaces ripple under internal pressures. Think of it like the deep, resonant tone of a cello string, vibrating in response to energy surging through the star. But here's the catch: the hum from Betelgeuse J004444, 86 plus 412,804, 6 is too steady, too uniform compared to other known stellar oscillations. Most hypergiants produce a cacophony of overlapping frequencies, but this one emits a single, unwavering note. Scientists have scrambled to explain it. One leading hypothesis suggests it could be caused by incredibly stable convection patterns deep within the star. Imagine a pot of water simmering at just the right temperature. Bubbles rise in perfect, unbroken rhythm. If the hypergiant's internal plasma flows are unusually orderly, they might generate this eerie hum. Another possibility involves magnetic fields. Hypergiants are known for their chaotic magnetism, but what if this star's fields are unusually structured, channeling energy into a single, coherent vibration? Then, of course, there's the elephant in the room: technosignatures. The hum's unnatural consistency has inevitably sparked wilder theories, from alien megastructures to advanced stellar engineering. While these ideas make for thrilling sci-fi, the reality is far more grounded. For one, natural cosmic phenomena often mimic artificial patterns. Think pulsars, which were initially mistaken for extraterrestrial beacons. Secondly, the hum lacks the telltale signatures of technology, like modulated frequencies or energy spikes. Still, the very fact that such theories emerge speaks to how profoundly unusual this signal is. What makes Betelgeuse J004444 86 plus 412,804 6 is so compelling is its challenge to our assumptions. If it's purely natural, it forces us to reconsider how hypergiants behave at their most stable extremes. If against all odds it weren't, it would upend our understanding of life's potential in the cosmos. For now, though, it remains one of space's most haunting melodies, a reminder that the universe still holds mysteries we've only begun to hear. Next, we'll unravel the lingering light echoes from VY 83 in M33, where the past seems to replay itself in the most unexpected ways. Don't go anywhere, this cosmic puzzle only gets stranger. Now let's turn our attention to a phenomenon where time itself seems to bend the ghostly light echoes of VY 83 in the Triangulum Galaxy. Unlike the steady hum we just explored, this signal is all about delayed reactions, cosmic shadows that linger long after the fireworks have faded. Imagine shouting into a canyon and hearing your voice bounce back seconds later, except here, the canyon is space itself, and the shout was a supernova-like explosion from the hypergiant VY 83. What makes this echo so puzzling isn't just its lag, but what it unveils about the star's surroundings. When VY 83 erupted, it unleashed a torrent of light that should have traveled outward in all directions at, well, the speed of light. But instead of fading uniformly, patches of brightness reappeared years later, as if something invisible, dust clouds, nebulae, or even strange gravitational lenses had caught and re-emitted the light like a celestial game of catch. These echoes aren't just pretty afterglows, they're forensic snapshots revealing structures we'd never see otherwise. Here's where it gets even weirder. The echoes aren't random. They form intricate patterns, suggesting the space around VY 83 is cluttered with dense, uneven material. One theory points to ancient shells of dust ejected by the star in earlier eruptions, layers upon layers of stellar debris acting like cosmic mirrors. Another idea involves interstellar filaments, thread-like clouds of gas that could scatter light in unpredictable ways, but the most tantalizing possibility. These echoes might hint at a previously unknown companion, perhaps a black hole or neutron star, whose gravity warps the path of light like a funhouse mirror. Of course, nature loves to humble our assumptions. What looks like a hidden object might just be the result of chaotic physics in the hypergiant's violent outflow. Yet every echo we analyze peels back another layer of VY 83 story, showing us how hypergiants don't just die dramatically, they leave behind clues in their wake, etched into the fabric of space and time. Up next, we'll confront the enigma of BSDL 2507, where the signals defy every stellar rulebook. Trust me, you won't want to miss this one. Now let's venture into one of the most baffling cases yet, the BSDL 2507 anomaly. This hypergiant doesn't just play by its own rules, it shreds the rulebook entirely. Unlike the eerie echoes of VY 83 or the rhythmic hums we've encountered, BSDL 2507 emits signals that refuse to fit into any known category of stellar behavior. It's as if the star is speaking in a language astrophysicists haven't even begun to decipher. First, let's talk about what makes these emissions so bizarre. Most hypergiants produce predictable radiation patterns, thermal X-rays from their coronas, radio waves from magnetic activity, or infrared from their dusty surroundings. But BSDL 2507, its signals flicker, spike, and vanish without any discernible rhythm. Some bursts last milliseconds, others linger for hours, and none correlate with the star's known cycles of rotation or eruptions. It's like tuning into a radio station where every second is a different genre of music, except here, the music might be rewriting our understanding of stellar physics. One leading theory points to exotic states of matter within the star's core. Under extreme temperatures and pressures, matter could behave in ways we've only theorized, like quark-gluon plasma, a primordial soup of particles that existed just after the Big Bang. If BSDL 2507 harbors such conditions, it might be generating bursts of energy as this unstable matter collapses and reforms. Think of it like a cosmic pressure cooker with occasional steam vents that don't follow any timer. Then there's the interstellar interference angle. Could something between us and BSDL 2507 be scrambling its signals? Dense molecular clouds or even rogue black holes might distort emissions, creating the illusion of erratic behavior. But here's the catch. No known interstellar medium can produce distortions this extreme without leaving other traces like telltale absorption lines in the star's light, and BSDL 2507 spectrum remains eerily clean. The most tantalizing possibility, BSDL 2507 might be interacting with an unseen companion, something stranger than a black hole or neutron star. Perhaps a magnetar with an off-the-charts magnetic field, or even a primordial object made of dark matter. These are the kinds of wild cards astronomers reluctantly consider when nature refuses to cooperate with textbook explanations. Whatever the truth, BSDL 2507 reminds us that hypergiants aren't just dying behemoths. They're cosmic laboratories pushing the limits of what we thought stars could do. And speaking of limits, our final mystery takes us to a hypergiant whose pulses are so uncanny, they'll leave you questioning everything. Stay tuned because what comes next defies even the wildest imagination. Now we arrive at the grand finale of Cosmic Oddities, and it might just be the most unnerving signal of them all. Picture this: a hypergiant star, still unnamed in the catalogs, broadcasting pulses so precise they seem almost intentional. These aren't random bursts or chaotic flares. They come in clusters with intervals and durations that eerily mimic Morse code. Before you let your imagination run wild, let's be clear, this isn't some interstellar SOS. The universe has a way of crafting patterns that fool even the sharpest minds, and this hypergiant is a master of illusion. What sets these pulses apart is their chilling regularity. Most stellar signals fluctuate with the star's turbulence, but these arrive like clockwork. Short bursts, long holds, repeated sequences like a metronome ticking in the void. Astronomers first dismissed it as equipment glitches, but multiple telescopes from the Atacama Desert to deep space observatories all picked up the same rhythm. The odds of a technical error replicating this pattern across instruments, virtually zero. So what's really going on here? The leading explanation points to magnetohydrodynamic waves, ripples in the star's plasma, shaped by monstrous magnetic fields. Imagine a guitar string vibrating, but instead of sound, it's emitting radio waves. Under certain conditions, these waves could produce structured pulses as they travel through twisted magnetic loops. It's nature's version of a cosmic drumbeat, one that just happens to resemble a code we invented. Then there's the rogue planet hypothesis. If an object, say, a super-Earth with a highly elliptical orbit, were skimming the hypergiant's atmosphere, its gravity might trigger periodic plasma ejections. Each close pass could pluck the star's magnetic field like a harp string, creating those measured pulses. But here's the problem. No such planet has been detected, and the star's colossal brightness makes hunting for dim companions nearly impossible. And yes, before you ask, scientists have ruled out more. Speculative origins. No, it's not aliens. The energy required to modulate a hypergiant's emissions would dwarf anything our civilization could muster. Plus, the signals lack the hallmarks of technology. No frequency hopping, no encrypted data. Just that relentless, unsettling pattern echoing across thousands of light years. This hypergiant's pulses are a humbling reminder. Even when the cosmos seems to whisper in a language we know, it's still playing by its own inscrutable rules. As we close this chapter on stellar mysteries, one truth stands clear. the universe is far stranger, far more inventive than we've dared to imagine. And that's what makes the hunt for answers so thrilling. As we wrap up this journey through the cosmos, let's take a moment to reflect on what these 25 unexplained signals from hypergiant stars have taught us. From the eerie Morse-like pulses of our final unnamed giant to the explosive bursts of Eta Carinae, each signal has peeled back another layer of mystery, revealing just how much we still don't understand about the universe. These aren't just random blips on a telescope's readout, they're cosmic puzzles, each one challenging our assumptions and pushing the boundaries of astrophysics. Think about it, the rhythmic whispers of VY Canis Majoris, the sudden radio silence of H Scorpii, the bizarre harmonic patterns from VX Sagittarii, none of these fit neatly into the textbooks. They defy our models, our equations, even our imagination, and that's the beauty of it. Every time we think we've got the universe figured out, it throws us another curveball, reminding us that the cosmos is far stranger and more dynamic than we've dared to dream. What ties all these signals together isn't just their mystery, but the humility they inspire. For all our technology and centuries of observation, we're still standing at the shoreline of an ocean whose depths we've barely glimpsed. These hypergiants, with their cryptic emissions, are like cosmic riddles, each one a clue to processes we're only beginning to decode. Whether it's magnetohydrodynamic waves sculpting pulses or rogue planets stirring up stellar atmospheres, the answers, when they come, will rewrite what we know about how stars live, die, and communicate across the void. But here's the exciting part: this isn't the end of the story. New telescopes like the Square Kilometre Array and the James Webb Space Telescope are coming online with the power to probe these mysteries like never before. Who knows, the next signal we detect might be the one that finally cracks the code, revealing a phenomenon so wild, it makes today's puzzles look like child's play. That's why I want to hear from you. Which of these 25 signals left you the most awestruck? Was it the haunting Morse-like pulses, the sudden silence of H Scorpii, or something else entirely? Drop your favorite in the comments below. I'd love to geek out over these cosmic oddities with you. And if you're as hooked on these mysteries as I am, don't forget to hit that subscribe button and ring the notification bell. The universe isn't done surprising us, and I can't wait to explore the next big discovery with you. Until then, keep looking up. The stars still have so many stories to tell.